So in problem 15, for us to find the derivative, we not only have to use the chain rule because we have things tracked, but we also have to use the product rule. So when I rewrite this, I'm going to rewrite it as 2 minus x. I'm going to put a visible multiplication dot to remind me to use the product rule. And then I'm going to write the x squared plus 8 in a 1/2 power. So remember, when you do that derivative, it's going to be the first piece times the derivative of the second plus the second times the derivative of the first. So the derivative is the first piece times the derivative of the second. Now when we do the derivative of x squared minus 8 to the 1/2, remember what has to happen. You're going to drop the 1/2 down, the stuff stays there, the power goes down by 1, and then you must multiply by the derivative of the stuff inside. And the derivative of x squared plus 8 is just 2x. Now that we've done the first times the derivative of the second, now let's do the second times the derivative of the first. And so write down your second piece, or the one you're not differentiating, and then multiply by the derivative of the first. Now the derivative of 2 minus x, the derivative of 2 is 0. The derivative of negative x is negative 1. Now read the question over. Always when you do these, just kind of take a look at what the question was asking. We want the first derivative when x is equal to 1. So now at this point, all of the x's become 1. So 2 minus 1 is 1. 1 plus 9, or 1 plus 8 is 9. So that's going to be 9 to the negative 1/2. We'll deal with that in a minute. 2 times 1 is 2. And then this is just going to be 9 to the 1/2. And then times negative. So that's your kind of first step. Remember, 1/2 powers designate square roots. Negative powers flip that thing over. So if we look at this, the 1, the 1/2, and the 2 just become a 1. So this becomes 1 over the square root of 9, so you get 1/3. And then this is a positive times a negative is a negative. And then this is just going to be a negative 3. Now, the answers that I'm going to give you will be fractional because I expect you to not use calculator or anything. And so just make everything thirds. This would be 1/3 minus 20, sorry, I'm getting ahead of myself, 27 thirds. No, it isn't.
No.
It's 9 thirds. And then when we subtract, we get negative 8 thirds. Okay? So there is number 15. Any questions about 15? So if you didn't know the product rule, if you didn't know the chain rule, that might be something you want to write down. Okay, make sure you understand how to use that. Now let's jump to number 16. It says find the equation of the tangent line to the curve defined by y equals 2x squared minus 5x plus 8 when x equals 2. There were some steps that we talked about when finding this equation of a tangent line. First step is find the first derivative. Second step, plug in to find the slope of the tangent. Third step, use y minus y1 equals m times x minus x1. So anytime a problem asks me to find the equation of a tangent line, that tends to be kind of the steps that I take. Okay? So the first thing we want to do is find the derivative of our function. So we're going to find the derivative of that y. And so y prime is just going to be 4x minus 5. Okay? It's just a polynomial. And then the second step is to plug in 2 to actually find that slope of our tangent. Because they said we're using when x is equal to 2. So if we plug in 2, the slope of the tangent is 8 minus 5, or 3. Now, as soon as we know the slope of our tangent, we can use that in the point-slope formula. But the point-slope formula needs a point and a slope, so make sure you have a full point. They didn't give us a full point, did they? They just gave us the x. But we can find the full point if I plug in 2 into the original, because it's a point on the original function. That would be 8 minus 10 plus 8, which is 6. So the point I'm going to use is 2, 6. I just plugged 2 into the original function. And the slope I'm going to use is 3. And now I just plug into the point-slope formula, and I got the equation of the line. Now, you might have to make it pretty, but let's do that. So it's y minus 6 equals 3 times x minus 2. And so we're almost done. Most of the time putting in slope-intercept form is usually the most often seen. So let's distribute the 3 and add 6 to both sides. And so we get y equals 3x. So there is 16. Any questions about 16? Okay. So that being said, what we just did in 16, what I would like you to do is I want you to give 17 and 18 a shot. And I'll do it too, and then we can kind of compare. Okay? So try 17 and 18 on your own. Don't peek until you're ready. And I'll get mine started too. Well, actually, just try 17, and then look up here and see if you got what I got. And then let's do 18 because 18 has implicit differentiation in it. We haven't done that in a while, so we can do 18 together. So if you check your 17 with my 17, when will a tangent line be parallel to y equals 3x minus 7? Well, when the slope of the tangent is equal to 3. So you'll notice I just took the first derivative, which represents the slope of the tangent, set it equal to 3, solved. Now, they wanted the point that it happens at. My x value is 2. When I plug it into the original, my y value is 6. It's the same equation for 16. So the point was 2, 6. Okay. So I'm sorry, I didn't see that 18 was implicit, and we haven't done that in a while. So let's do implicit differentiation together. Let me write the equation down below here.
Scroll up a little bit.
Yeah. Let me move. If I move the cursor, that will help. Okay. Okay, so the problem 18 said, find the slope of the tangent line of the equation given at the point 2, negative 3. Okay, so that was the instructions. The slope of the tangent is always the first derivative. So you should know that and have those two linked in your brain. So we need to find y prime. Now, in this case, you'll notice that the x's and y's are all mushed together. And did I write it down right? Yeah. So since the x's and y's are all mushed together, anytime they're touching, put a little dot between them to remind you that you must use the product rule, and that every time you take a derivative of y, you're going to put a little stuff there, that y prime. Okay, it's like a chain rule. So let's go through the process. So the derivative is 2x plus. Now, this piece has lots to it because it's going to be a product. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. So it's going to be the first times the derivative of the second. Well, the derivative of y squared is 2y times the derivative of the stuff, which is y prime, okay, plus the second times the derivative of the first. The derivative of 2x is 2. The derivative of 3y is 3y prime. The derivative of 31 is 0. So that is our first derivative. Okay. Now we want to know what the slope of the tangent is at the point 2, negative 3. So now what's great is we have an equation with x's and y's and y primes in them, but we have the x and the y. So every place we see an x, we're going to put a 2. Y's are going to be a negative 3. We'll be able to find y prime, okay? So we're going to get 2 times 4. Now, this is going to be 2 times 2 times 2 times negative 3. So all that there is going to be 2 times 2 times 2 times negative 3. That's going to be 8 times negative 3, or negative 24. This is going to be negative 3 squared, which is 9. 9 times 2 is 18. So now we only have y primes left. So it's just a standard normal equation to solve for y primes. So let's put the y primes together and the normal things together. 4 plus 18 is 22. Negative 24 plus 3 is negative 21. Let's move the y to the other side to make it positive. You don't have to. Divide off the 21. So that is the slope of our tangent. 22 over 21. So there's 18. Any particular questions about that one? Just making little light bulbs remind you of the stuff we did quite a while ago? Yes?
So how do you do the derivative of 2x times y squared?
We had to do the product rule. So these pieces right here are the product rule. Let me take you through it one more time. It is the first times the derivative of the second plus the second times the derivative of the first. So I made this the first, 2x. I made this the second, y squared. You have to use the product rule. It's an implicit. When the x's and y's are touching, you have to use implicit differentiation and split them up and make them a product. Okay, so now 27 is the exact same kind of problem. Exactly. So I want you guys to try 27. I'm going to let you do it on your own. Everybody, let's try 27. And then I'll take you through the process so we can check it. Let's try 27. I have my first derivative up on the board if you want to check what you got compared to what I got. This part right here is my product rule. I highlighted my product rule in yellow. Anybody have any questions about 27? Answer is -9/2. Hopefully you got that. Let's take a look at 28, 29, and 31. Now, it's all about recognizing they have done the derivatives for you. But you have to remember, what did the derivatives tell me? So remember, the first derivative is your slope of your tangent. Where the first derivative is positive, it's going to tell you where it's increasing. Where it's negative, it's going to be decreasing. The second derivative tells you, remember, about inflection points and concavity. Where the second derivative is positive, it's going to be concave up. Where the second derivative is negative, it's going to be concave down. So let's use that information. And if you didn't know that, you might want to write that down. For 28, it says find the intervals on which f is increasing. So for increasing, we do not care about the second derivative. So we're only going to be focusing on what's happening at the first derivative. So that's the plus and minus chart that you guys know and love so very well. You're going to take and set each piece equal to 0. So we can make our plus minus chart. So we get 0 and 3/4. We're going to make a little chart. Make a number line, put them in least to greatest order. Now these are just polynomial points. They exist. They're wonderful. Put a closed off. And now put the factors on the side, x squared and 4x minus 3. Then we're going to have test points. So let's go -1, 1/2, and 1. Anything that is in the interval before 0, between 0 and 3/4, and after 3/4. So we get, for x squared, we always get positives. For 4x minus 3, we get negative, negative, positive. And so we get a negative, and a positive. Now they said increasing. So the only part on our plus minus chart that is positive or increasing is this part right here. So the answer would be when x is greater than 3/4. You can also do the from 3/4 to. Now you don't include increasing or decreasing with a bracket because of the fact that we're not landing at that point, or that point is a switchover between the increasing and decreasing, and so you don't have to include it in concavity, increasing and decreasing. You usually just use parentheses, okay? Any questions about 28, intervals of increasing? So if they wanted intervals of decreasing, we would be anything below 3/4. Okay, let's take a look now at 29. 29, they're asking for intervals on which the function is decreasing. So scratch out the second derivative. You don't care, you don't need it, it isn't going to help you, it isn't something you need. All we care about is the factors of the first derivative. So we're going to take the top and set it equal to 0. We're going to take the bottom, set it equal to 0. We're going to get 1 for the top and -3/2 for the bottom. We're going to make a plus-minus chart. Put it in least to greatest order on the number line. The bottoms always get open circles. The tops always get closed. Just because you know one is an asymptote and one is a point of inflection or a critical point. Okay. Let's turn this into a chart. We list all the factors from the top and all the factors from the bottom. We're going to pick out some testers. So why not? Let's go -2, 0, and 2. Anything within those intervals there. If we plug, let's plug in everything to the top. We get negative, negative, positive. Let's plug now everything into 2x plus 3. We get negative, positive, positive. And now let's divide them. Well, if we have a negative divided by a negative, that's a positive. A negative divided by a positive is a negative. Positive divided by a positive is positive. Now think about it. This time we want decreasing. So what do we want? Positives or negatives? We want decreasing. What do we want? We want the negatives. So let's color those in. So we want anything from -3/2 to 1. So that is our answer for 29. Any questions about that one? Okay, let's do 31. This time they're talking about concavity. Remember, concave up and down is determined where the second derivative things are happening. So let's scratch out the first derivative so we don't use that. And let's focus on our second derivative. Let me move this down out of your way. So for 31, it is concave down where the second derivative is negative. So we have to do the same exact thing, a plus or minus chart. Now, it's not fully in factored form, so let's get it in factored form. This is technically 6x over x plus 2 cubed and x minus 2 cubed. Now, why is that? Well, x squared minus 4 is x plus 2 times x minus 2, and there's 3 of each of those. Now, you can write it lots of ways, but I think that's the most efficient way to write it. Now, how do we determine how to make our plus or minus chart? Well, we take all the factors, set them each individually equal to 0, put it on a number line. I think you know that by now, but let's do this. So where does 6x equal 0? That's at 0. Where does x plus 2 cubed equal 0? Well, the same place where x plus 2 equals 0, or -2. And so x minus 2 cubed is where x minus 2 equals 0, or x equals +2. So when we make our plus and minus chart, we have -2, 0, and +2. Now the factors from the bottom, here and here, make them open circles to remember those are not points on our graph. They are an asymptote or something like that that is interfering in our graph. The top is. That might be an inflection point. Make it a chart. We have 3 factors. 6x, x plus 2, please include the cube, x minus 2, please include, I can't say include the cube, say that, that's not okay, now let's try to think of some good values to plug in. So let's just go negative 3, negative 1, 1, and 3. Can they be anything? Of course they can. I'm just picking things I think are nice to plug in. Okay. Now let's plug in our values. I'm going to focus just plugging them into 6x. So I'm just going to go down the list. I'm going to keep using 6x. I'm going to get a negative, a positive, a positive. Now let's plug into x plus 2. Now let's think about if I cube it. If I cube a negative, it's going to stay negative. If I cube a positive, it's going to stay positive. So the cube is somewhat irrelevant, but it's important. I like to keep it there because what if it was a square? That would be important. So I just always include it. If it's odd, it's not going to change anything. If it's even, it will change some stuff. So if we plug in negative 3, we're going to get negative 1, cube it, get negative 1. Plug in negative 1, we get a positive 1, cube it, still positive. Still positive, still positive. Now let's do the same thing for our x minus 2 cubed. So we're going to get a negative, a negative, a negative, and then a positive. And now these are either multiplied or divide, so just do, I have this many negatives. And so 3 negatives are going to make that section negative. 2 negatives become a positive. 1 negative becomes a negative. All positives stay positive. Now, remember, go back to the question. We want to concave down, which is where the second derivative is negative. So color in the negatives. And that's our answer. So it is concave down from negative infinity to negative 2 and from 0 to 2. Any questions about that one? Are you remembering stuff? Okay. Next one's on our list for 34, 36, and 39 on this page. Yes?
I do have a question.
Sure.
So say if there was a negative on one side and on one side, and there was an open circle, and there was a negative on the other side. Do you get to have them as two separate points?
Yes, you do. So if they're separated by an asymptote, you do need to designate that separation.
Okay.
So you do want to write it as separate intervals. That's another way that I tell myself to not forget that point, because that open circle will remind me, hey, I can't include that. It is a separation into a new interval. Now, if it's colored in and then there's a closed-in dot and it's still colored in, then you don't have to worry about it.
Okay.
But if it's an open circle, please don't include it. Okay, so let's get 34 here. Okay, so let's do 34. So, local minimi, those are just fancy way of saying the minimums for the local minimums. Remember, that's max and mins are about the first derivative. So we have to do the first derivative and do a first derivative chart. So the first thing, when they ask you to find the local minimi or maximi, whichever they ask you to find, take the first derivative. So remember, the 3 drops down in front, multiplies by the 1/3, you get x squared. 2 drops down in front, that's a 6x plus 1. Now, that is, it's not a factor of a quantity. So it's either going to be all positive or all negative. It's either going to be all max or there's not a local max. We're going to cheat a little bit. I don't know why they would give us this one. That's kind of dumb. let's just look at the graph for a minute. Yeah, there is a point. There's a local max. Or is it they wanted a minimum? Local minimum. Yeah, there's a local minimum. Did I did I do the derivative wrong somewhere? That's the correct derivative, isn't it?
Yeah.
It's not factorable, is it? No. Okay, let's do the quadratic form. Well,
I don't know how 1 times 1 gets you 6.
yeah. Well, no. I know it's not factorable. That's why I'm questioning what's going on in my brain.
Is F-
Okay.
F prime of x correct?
Uh-huh. Okay, let's put that in.
Well, that's you playing games.
Hey, Arthur, you're messing with my brain.
Wait a second. So you have, okay, so f prime, you have x squared right there. Are you sure that's correct, coming off of 1/3 x to the third?
Uh-huh.
Yeah, 3 times 1/3.
Yeah.
Yeah, then you have to divide it by 3.
Yeah.
No, you're not integrating.
Cancel
So you
each
drop
other
down
out.
what I'm trying to say, don't you drop down the 3, so it's 3 over
It's
3
3
3
times.
over 3, and then
3
you also
times
divide it
1/3.
by 3 since you drop down the
No, it's 3 times 1/3.
I
Okay,
understand that.
stop. There's got to be.
It's
Let's
in
do the
addition
quadratic
to
formula. Okay. No, it's going to be disgusting, isn't
Why don't we just
Okay.
skip this one? Like,
it?
give the old college try.
Negative b plus or minus the square root of b squared minus 4 times a times c all over 2a's. Yeah. Why are we not thinking of this correctly? Wait. You see all the weird things I do. Let's see here. Okay. I didn't. Did anybody get the detailed solutions out of Classroom?
You already know I have them. Which number are we looking at? 34?
Yeah.
Alright. 34. Well, it shows that there's a second f prime they have out for some reason, which is 2x plus 6, but it doesn't look like you do anything with it. Yeah, they use the quadratic formula and get negative 3 plus or minus.
So they did what
2
I did.
radical 2. And then you get, when they are
Did they do the plus and minus term?
No. When they're
No,
over
they
here
put
with
it in the.
f second primer.
Oh, they did. Okay. So let me go back. So so these are the critical numbers. So there must be a minimum and a maximum of those things. Is my And if making a plus or minus chart because you don't have a calculator would be tough. Now square root of 2 is 1.4, so you could kind of gauge what that is if you knew that was 1.4. I don't know, but anyway. If you took the second derivative, do you guys remember that there was a second derivative test for maxes and mins, and if you plugged into the first derivative and got a positive, it's concave up, so it must be a minimum.
They
If you
the
plug
first
in-
derivative into the second derivative.
Uh-huh. So if you plug the critical numbers from the first derivative into the second derivative and you get a negative, it's in a concave up spot. No, if you get a positive, it's in a concave up spot. So it has to be a minimum.
Positive
So-
is a minimum, negative is a maximum.
Yeah, it's kind of the opposite of what you would think. So the first derivative, being what it was, would give us a second derivative of that. If you plug in negative 3 minus 2 square root of 2, you get a negative. So it's concave down, and that's the positive. That's the max. But if you plug in negative 3 plus 2 square root of 2, that's going to give you a positive. So it's a minimum. So that is the minimum. And that is the maximum. When I gave you ones about maxes or mins, I always made sure that they were factorable quantities. You could make the plus minus chart very clearly. So sorry about that one. I was on the right track, but I just was questioning. Like, what? So yeah, I did make mine. Mine are factorable, so you'll be okay when the time comes. Okay. Okay. Let's see. 35. Now these ones are the max and min on an interval are actually clearer and nicer than just, hey, find all of the local mins and maxes. Okay? And this is why. Let's talk about the procedure for when it's on an interval. You're going to take the first derivative. You're going to find the critical numbers of the first derivative. So you're going to set that first derivative equal to 0. You're going to solve. Now, the first interval that they gave us was 0 to 3. Okay? Which one of those numbers is in the interval from 0 to 3? Is positive 2, negative 2, or both of them? Because possibly it's both of them. Maybe it's neither of them. Oh, I'm sorry. From 0. So from 0 to 3, the interval that's in there is also 2. So remember, you're going to plug back into the original, the endpoints, and also the critical numbers that are in there. So we can't use negative 2. We can only use positive 2. So when we do the problem the first time on the interval from 0 to 3, we use 0, 3, and 2. Now, we're always remember, one of the things I remember when you took a test on this stuff is you didn't plug back into the original. We're looking at the maxes and mins for the original. So if we plug 0 in, we get 0. If we plug 3 in, we get 8 minus 36, which is negative 24. If we plug, no we don't. Yeah, it was. What the heck? That's 27 minus 36, or negative 9. And then that's 8 minus 24, or negative 16. So then you just label what's the max. Well, the largest of all of those is 0. And what's the minimum? Well, that's negative 16. Now, sometimes they say, where does the maximum occur? And they'll just want the x's. Sometimes they'll say, what is the max or min? And then they want the values. Now, if we repeat the problem, this time on the interval from negative 3 to 0, we only include the endpoints, negative 3 and 0. And the only critical number that's in there this time is negative 2. So you got to be careful with that. If you plug in negative 3, you get negative 8. No, you don't, my God. If you plug in negative 3, you get negative 27 plus 36, or 9. Plug in 0, you get 0. Plug in negative 2, you get negative 8 plus 24, which is 16. This time our max is 16 and our minimum is 0. So it could switch around depending on the interval.
Plugging it into
The original function. See how I just have it labeled as f? We're plugging it back into the original.
okay.
So for intervals, you're plugging it back into the original. Max and min on an interval, always plug it back into the original. that's from that page. Oh, 39. Let's do it. So if you're doing a maximum problem, whether it is a word problem or it is on an interval or it is on a regular thing, and maximum, you remember, is related to the first derivative. So when you read a problem like this, and it mentions the word largest or maximum, you got to think, I have to find an equation and take the first derivative. Do a plus or minus chart or something like that. Okay. So let's set up 39. It says, what is the maximum area that can be enclosed by 200 feet of fencing if the enclosure is in the shape of a rectangle? So I usually don't go any further, and I draw a rectangle. And it says one side requires no fencing. Okay. So then I put, let's make this X. No. So what do we know? Well, we know that we have 200 feet of fencing. So the perimeter, the outside edge. If I walk along this, if I'm a little ant and I'm walking along this, I go an X length, then a Y length, then an X length. So the perimeter is 2x plus y, and that length is a total of 200 feet. So they're going to give you one piece of information about your materials, usually how much of something you have. And then one information they're going to give you for the thing you're trying to maximize. Well, we're trying to maximize area. But they gave us a hint. They told us it was a rectangle. Yes?
Is this the same question we had on that one quiz we had?
I think so.
Yeah, that really made everyone just off themselves.
So the area of a rectangle is length times width. In this case, x and y. Now, when we did these problems, we talked about the fact you want to use only one variable. So they had to give you some information to allow for a substitution. And this equation here, I could do a little rewrite and write it as y equals 200 minus 2x. So I can put that in for y and get a much nicer thing to differentiate because I need one variable, not two. So the area is x times 200 minus 2x, or the area is 200x minus 2x squared. When I write 200 fast, it looks funny. Okay. How do we find the max of something? Take its first derivative, make a plus or minus chart, look and see what's the max going up and down, and what's a min going, Okay. So, first derivative is related to the max. So let's do the first derivative. So the derivative is 200 minus 4x. We need a plus or minus chart. That's our only number. So if I were a guessing person, whatever I get for this is going to be my maximum. But that's 200 equals 4x. X equals 25. Now, I always read the question because if I made this test up, I'd put 25 as an answer. But that's not the answer they want. Read the question. What is the maximum area that we can enclose? So the dimensions of this is 25. Y is 200 minus 2 25s, or 200 minus 50, or 150. The maximum area is 150 times 25. And it would be square feet because it's area.
What does it say? A prime equals 2 something minus 4x.
200 minus
What
4.
x
Oh, that's 200.
Say that again?
What x would
Yes, it sure would be. I even wondered, that's kind of a little number. Thank you.
I knew it. I
thought I was going insane. 'Cause
Thank
I
you.
literally looked at this problem. I'm like, oh,
That's enough.
that's easy.
I think she deserves bonus points, you know.
This problem is too complex for the solution. Like, you just look at it and know.
What's the answer?
5,000.
Well, not that part, just the x's and y's.
I swear I put that on the test. I might have thought it, but
I don't know if it's exactly this one because I think mine had some.
I think
lines
it's
down the middle.
I think it's the exact same one.
I don't remember.
Because Anthony and I were talking about it. We're like, we're just going to leave it blank.
Complex reads.
So that is 39. Let's see where we left off. Okay.
Go back to 30.
Yeah. Let me give you a chance to copy that down.
I have 6 left.
Yeah, we're getting close, aren't we?
That's great. Sure, we'll have to do all these for the
Yeah, I was gonna say you need to study them.
Oh, yeah.
Just because I can do them for you
No, I
doesn't.
know, I'm just saying, like, we only have 6 left.
Okay. So now we're gonna do 52. I so suck at circling this thing. Okay, so it says in each of the following, determine whether intermediate value theorem guarantees a solution to the equation in the specified interval. The intermediate value theorem guarantees a solution, or the fact that if it equals 0, if the function is continuous on that interval, and when you plug in one end of the interval, it's negative, and the other end is positive, or vice versa. That's all you got to check. There's no derivatives you have to do. There's no nothing. And when you guys miss these problems, I'm always like, oh, but this is an easy one. Okay, so let's start with A. So let's call, it has to be equal to 0, and it has to be continuous. That's a polynomial. It's continuous from 1 to 2. There's no breaks, holes, jumps, gaps. Okay, now we're going to call that f of x. We're going to plug in 1. We're going to plug in 2. If one of the values is positive or one of the values is negative, you say yes. If they're both the same sign, no, we don't necessarily know there's a 0 in there. Okay, so let's plug in 1. We get 1 plus 2 minus 10 plus 5. We get negative 2. Let's plug in 2. We get 32 plus 8 minus 20 plus 5, which is positive 25. Since they switched, the answer is yes. There's a solution. There has to be a 0 in there. Because if it's a continuous function, there's a piece of string like that connected the point 1, negative 2 to the point 2, 25. Don't you have to cross over 0? That's what the intermediate value theorem says. Okay, so that's a yes. Now the problem with B is, are we equal to 0? No. So the first thing we want to do with B, let's move the 5. Let's call that f of x. Now is it continuous? Oh, sorry, that's a x. Is it continuous? Well, between 4 and 9, a square root is continuous, because it's just continuous on the positives. So it's fine. So if we plug in 4, we get 4 minus 2 minus 5, which is negative 3. If we plug in 9, we get 9 minus 3 minus 5, which is 1. That's a yes again. Let's look at C. Got to move the cosine over, or either one. Cosine is a continuous curve. X is a continuous curve. Put them together, they're continuous. So it's continuous. Now we just have to check, do the intervals do what we want the intervals to do? So let's call this f of x. Let's plug in 0 and pi. If I plug in 0, I got 0 minus the cosine of 0. That's 0 minus 1, which is negative 1. If I plug in pi, I get pi minus the cosine of pi. That's going to be pi plus 1, which is a positive. One's negative, one's positive. It's a yes. D. The tangent has a gap. But where is the tangent undefined? Well, the tangent's undefined where the sine is equal to 0, which is pi over 2. Is pi over 2 in there? Is pi over 2 between pi over 4 and 3 pi over 4? Between a fourth and 3/4? Yeah. So this would be a no right off the bat because I don't even have to try it. It is not a continuous function because tangent of pi tangent of pi over 2 is the problem. So that would be a no. So that is 52. So make sure it's equal to 0, plug in the ends. If one is positive, one is negative, then yes, there has to be a solution within that window. Did they ask you to solve for it? No. Do you know it's there? Yes. Where? I don't know. So that is 52. Okay. Let's look at some of the integration ones. So we're going to do 58A. So it just says to integrate. Since this is trapped, you don't want to have to take that thing out to the fourth and then take and multiply by x and then finally get to do an antiderivative. Since it's trapped, you need to check to see if it's a possible u substitution. This is the way you know whether u substitution is going to work. Is this 1 degree higher than what's outside? So it's probably a u substitution. So what is the u? Well, the u, 99% of the time, is going to be the thing trapped inside. So trapped inside of that fourth power is 3x squared plus 4. Now remember what we do. We take the derivative in terms of x. So this is du dx equals 6x. Now, what do we have to substitute? Well, we already know that this is u. We need to know what is x dx equal to. That's our other stuff in the problem that needs substituting. So we need the x dx on one side and everything else on the other side. So if we get the x dx on that side, the 1/6 comes from the fact I had to move the 6 to the other side. So x dx is equivalent to 1/6 du. So we get 1/6 u to the 4th du. Now it just becomes a standard antiderivative. Ignoring the 1/6, what is the antiderivative of u to the 4th? What is the antiderivative of u to the 4th? So the power goes up by 1, and we divide. What's our antiderivative?
It would be 1/4, 1/5 u to the 5th.
Yep. Or you can even write it as u5 over 5, sometimes is what I'll do it. Now, the original problem had x's in it, so the last step is to put the x's back in. U gets taken out and replaced with 3x squared plus 4. So we get 1/30 3x squared plus 4 to the 5th. Sometimes you'll even see it written 3x squared plus 4 to the 5th all over 30. That's okay too. So there is that one for you. Let's do this one. I'm going to do this one right next to it. I think I have enough room. For this problem, do you remember when we were doing derivatives? If there was a way to do a rewrite so that things became nicer, before you took the antiderivative, you always want to do that rewrite. And so there's a little rewrite here. Because this is a monomial, let's divide it into all three pieces. And so I'm going to integrate 3x to the negative 2 plus 6x to the negative 3 plus 2x to the negative 4. Now the reason I can do that is because if this is a monomial, I can divide it into each individual term. And that's just taking 4 off the power of each of those. So then remember what we're going to do. We're going to antiderivative. So the power goes up by 1 and we divide by the power. Opposite of a derivative. So the power goes up by 1 and I divide by that power. The power goes up by 1 and I divide by that power. The power goes up by 1 and I divide by that power. And then put your little plus c. Now let's just make that look just a touch nicer. Okay, so our final answer would be negative 3 over x minus 3 over x squared minus 2 over 3x. Yes.
For this, do we have to include C as our answer?
The test is multiple choice. So the C's, if I remembered them, will be typed up in the answer. But it's just traditional. You're supposed to put that plus C because there could have been any constant sitting there. But I won't. Yeah, I won't. You know, when I look at your work, try to remember to put that C in. Let's do N. N is an interesting one. There's two ways to approach it. What's the derivative of a tangent?
Secant squared.
Secant squared, right? And so I see a tangent and I see its derivative right there. So to me, that does require a u substitution. I'm going to let u equal the thing where its derivative is. Its derivative is in the problem. Secant squared is in the problem. Because when I do du dx, I get secant squared, which is a perfect u substitution. So du is the secant squared of x dx. So this right here is du. This right here is u. So it becomes a very easy derivative really quickly. So we get the integral of u du. What is the integral of u to the first? Well, the power has to go by 1, right? And you divide by that new power. So what's the power going to go up to? A 2, right? And then, so this is going to be u squared divided by 2 plus c. Now, what was the u? The tangent. What do we got to put back in? The tangent. And so our answer would be the tangent of x squared over 2. I think there's an alternate answer. But I'll think about it. I'll let you know. Because the derivative of secant is secant tangent, and that's there too. And the antiderivative, what's the antiderivative of secant? No. It doesn't have an end. Okay, never mind. Well, we'll leave it like it is. It worked. We're going to say it's beautiful. Okay. Let's keep going. What's after 60 and 61? Did I pick any other ones?
61 are the last ones.
What? Mine goes to 73.
No. The ones I circled in red.
You can still do the ones at 73. It's okay.
Okay. So we'll do 60 and 61 now. And then I'll let you study a little bit. And then when we have our Google Meet, I think I'm going to do a few more. I think I'll do one volume and one average value. I don't know. I'll look and see. Okay. So let's do 60 and 60. Let's do the areas and then we'll stop for today. Okay. Anytime they ask you to find the area between two curves, you have to have at least a fairly accurate graph. Okay, so let's start with 60. We have y equals x squared and y equals x to the 4th. Now it's not a bad idea to set them equal to each other, solve them to make sure you know at the exact points at which they meet. So they meet at 0 and plus or minus 1. If you were to graph them, and I know this isn't going to be the greatest picture, but so x squared looks like this. X to the 4th almost looks exactly like it, but it's actually a little bit lower, and then it gets higher. Now, how can you test that? Well, you could plug in a half. 1/2 squared is 1/4, but 1/2 cubed, or to the 4th power, is 1/16. So it's even lower. It's closer to the x-axis. So this is your x to the 4th, and this is your x squared. So the x squared is actually a little higher in the middle and lower on the ends. And the x to the 4th is lower in the middle until it hits 1 and then higher from there on. So what I would do for this, they want the area, this area. But isn't the area on the left exactly symmetric with the area on the right? Because they're both even functions. So why not double up the area from 0 to 1? Our top function is always x squared. Our bottom function is always x to the 4th. Now, you have to remember, it's always top function minus bottom function. If they ever flip positions, you start the integral over. Or you could cancel some area out. Always top function minus bottom function. So it's just antiderivatives. So the antiderivative of x squared is x cubed over 3. X to the 4th is going to become x5 over 5. If I plug in 1, I get 1/3 minus 1/5. If I plug in 0, I get 0. I like to just write that for my own peace of mind that I know I checked that 0 is really going to get me 0. That is 5/15 minus 3/15. That's 2/15 times 2 is 4/15. So there's 60. I'll let you copy that down and then we'll do 60. That's all I do. Just trying to make it bigger. There we go. Any questions about 60 before we move on to 61? Yeah, definitely. I'll make it a little bit. Yes. Yeah, go ahead. Okay, let's try 61. Are you ready, Nate? All good? Okay, 61. So I know that the one is a parabola and the one is a line. But I really just looking at them, I'm a little unsure of where those things meet up. So the first thing I would do for this problem is, where does x squared equal 2 minus x? Well, that is a parabola. And so the best way to solve a parabolic equation is get it equal to 0. So this comes over and becomes a positive x. This comes over and becomes a negative 2. So we get x plus 2 and x minus 1 equals 0. So they hit at two places, negative 2, and they also meet up at positive 1. So those points become very important on my graph. So let's draw our graph. So let's think about the line y equals 2 minus x. If you plug in negative 2, you get negative 2, 4. And if you plug in 1, you get 1. And it's just the line with the slope of negative 1 that has a y-intercept of 2. And you can kind of see that. Okay, so there's our line. And then the other is just the standard normal parent parabola. So 0, 0, 1, 1, 2 goes up to 4, and so on. So you can see that the area between the curves, the line is always the top function, and the parabola is always the bottom. So the area is just going to go from negative 2 to 1. See how important those numbers were? Because they show up as the boundaries on our integral. And it's going to be the top function, 2 minus x, minus the bottom function, x squared. If the bottom function was the line, make sure to put it in parentheses so you distribute properly. And then we antiderivative. So we're going to get 2x minus x squared over 2 minus x cubed over 3 from 1 to negative 2. Now remember, it's the top boundary minus when you plug in the bottom boundary. We are going to get some values here because it wasn't 0 that they met up at. If we plug in 1, we get 2 minus a half minus a third. Now let's plug in negative 2, so you've got to be careful. This is going to be negative 4. That's going to be 4 divided by 2, which is 2, so that's going to be minus 2. And that's going to be plus 8 thirds. So then I'll distribute, well, let's make this a negative 6. Okay. So I get 2 minus a half minus a third. Minus a negative 6 would be plus 6. Minus an 8 thirds. Oh, I don't know. Let's put together things. 8 minus a half minus 9 thirds. That's 3. I'm sorry, I'm talking to myself here. And then that's 5 minus a half, which is 4 1/2. Or you could do, you could also do 9 halves. I don't know. I just put stuff together. So that's a good chunk of stuff that you want to study. Tomorrow I'll talk about any other pieces and parts that you need to study. That's basically that.